All right, so we're coming up on the season finale of this chunk of these lectures. And what I mean by this is that what we've been doing is something that is very different than what we're going to be doing. What we've been doing is just kind of developing this Turing model on its own, the single model of computation. And one thing we've kind of gotten to, one thing that I think I've hopefully convinced you of at this point, is that this model is very exhaustive in several ways. One, it's exhaustive in the sense that it seems like no matter what we do to it, it seems like if we add more tape strings, if we give it new bells and whistles, it seems like no matter what we try to do, despite how simple it kind of seems at the surface, at least in terms of concept, we never get anything new. We never get a more powerful machine. If I add more tapes, I can just collapse it down. There's a way to simulate that with a single tape machine. If I add more, anything, right? If I add a tape that can extend in two directions, and there's other proofs I could have done there. I could have proven to you that, if you had a single cursor in like graph paper, like actual graph paper, you could move in 8 ways, or whatever, that wouldn't be anything more powerful. And hopefully I don't even need to do that. Hopefully you can just see that there would be a way to deal with that. There would be a way to mess around with that and make it work. So it's exhaustive in that sense. Another sense in which the model is exhaustive is that its initial premise, its initial promise was that it was the kind of formalization and sort of captured the essence of the idea of a person with paper and a pencil thinking and writing on a paper and interacting with those things that he's written down. Right? It was the original idea was a very natural one in terms of not capturing the idea of a computer, but an idea of just algorithmic thought as a whole. And so, given those two things combined, you should be somewhat convinced that this Turing model is at least robust enough to tackle any problem that you could tackle with your own favorite programming language. If you can do it in C, if you can do it on paper, if you can do it however you want, then you can probably make a Turing machine that does it. Hopefully I've convinced you of that through this exhaustive, kind of admittedly boring collection of lectures so far. But I felt like it was important to do that. The one thing we have left to do is we need to make a universal Turing machine. So even despite all of that, even despite its potential for problem solving, this machine probably still kind of seems weaker to you than what you typically view as a computer. Now, why is that? Well, the reason for that is that your computer is very special in that what we think of as modern computers, the computer in front of me, the computer in front of you, these are special machines that are with the capability of simulating other machines. This you're running a program, an operating system, that has the potential to run potentially any other program, any other machine. What you have in front of you is a machine that can simulate other machines. The machines that we've been making so far are machines that solve very specific problems. I make a problem to solve the palindrome problem. I make a machine to add 2 numbers. I make a machine to do this or do that. I make a machine to do something specific. But the machines that you're used to thinking of as computers are kind of more powerful than that. They can simulate any of those machines that we've been talking about. And that's what I mean by universal. A universal machine is a machine that can simulate other machines within its model. And in some sense, this is as much the standard bearer of a competent model of computation as its ability to solve problems. You kind of have a competent model of computation if your model of computation is sophisticated enough that you can build out of it a particular example of something that can run other machines in the model. So you have a really competent model of computation if you can build a universal machine in your model. So that's what we need to do. In order to kind of convince you that we have like a fully developed model of computation, we really need to create a universal Turing machine. Okay, so we will denote our universal Turing machine, and what I'll usually write is UTM, U. The machine, U is going to be a machine that takes 2 inputs. First input is another machine. I'll call it M. And the second is an input to M. It's an input to that machine. So it takes a machine, and then it takes an input to that machine. Is an input to that machine. I'll call it X. And so basically what a universal Turing machine is going to do, the defining kind of idea of a universal Turing machine is that U of M, I'll put like usually you put like a comma in between inputs, but this is a very big input, so to separate it out, I'll put like a semicolon. But it's really just M comma X is equal to M of X. So what it does is U takes a machine and an input, and what it does is it simulates the machine M on that input, X. This is what it means to be a universal Turing machine. So obviously there's kind of a bit of a weird thing going on here, right? But what is the input to a Turing machine in general? The input to a Turing machine is a string. So but I've sort of broken that convention here. I've said the input to this Turing machine is a string X, but then another Turing machine. A Turing machine isn't a string, is it? Well, no, it isn't. So what we really need is we need to find a way to encode a Turing machine description as a string. So in a way, this is going to be a string. This is really a string representing the complete description of a Turing machine. And you should think of it as a program, right? If this is what this really is it's a set of characters. It's a big string that represents a machine, a computational process. And so this is really the way that you think about it. You should think of this as a program. You should think of it as a program. So what this computer takes is it takes a program. I've written a program in some language that is the language of Turing machines, and then I've given an input to that program. So you should think of this as the program. And what we need now is a standard we need a standard method of how to do this. So we need a standard method of encoding complete descriptions of machines with a finite string. So first of all, can we do that? Well, of course we can. So can this be done? Certainly, and I think you can believe that, but it's something that I haven't talked about yet, and it's incredibly important, and so this is a good time for me to talk about it. You know, Turing machines are fundamentally finite in the sense that I can describe them in a finite way. I mean, I've written down lots of Turing machines, like the complete description of lots of Turing machines at this point. Right? Just think about the palindrome problem. How do we make a Turing machine for the palindrome problem? I wrote down on my screen everything involved. I also gave you a complete Turing machine when I was giving you that Turing machine that did the space creating subroutine. Right? That was I just gave you a table, and just we can kind of think about it. Right? Like if you have a machine M, which is sigma q delta, this thing is finite. This is a finite set of characters. This is a finite set of states. And then this is a little more complicated, but it's a function whose inputs are sigma state, are symbol state pairs. And so as a function, you can completely define a function by just completely defining what it does at each of the inputs. And so how many inputs are there? Well, there's this many times this many. Sorry, there's this many times this many. So the transition function is just a finite list as well. It's a finite list of function inputs and outputs. So this whole thing, this is a very finite description. This is kind of itself a finite description. I just need a way to standardize how I'm going to represent it as a string in some alphabet. But fundamentally, this is already a finite description. And think about what it does, right? A Turing machine, despite being finite, a Turing machine decides a language, which is infinite. So what it does, what a Turing machine really is, in kind of a more like linguistic sense. So a Turing machine is, in some kind of fundamental sense, in a kind of foundational way, kind of to divorce what we've been doing kind of from computability entirely, is to say that a Turing machine, really what it is it's a finite description of an infinite set. It's an infinite set that I'm specifying in a finite way. I have a problem, and if I have a Turing machine that halts on every input, that specifies a set that completely describes an infinite set in a finite way. So that's kind of what a Turing machine kind of is in kind of a divorced sense from computability theory. To what extent can I describe a language within a finite way? And so that's kind of deeply connected to Turing machines. So anyway, what we need to do now is just kind of standardize it for the sake of creating our Turing machine. So the alphabet for U, we're going to make it this. It's going to have a 0 and a 1. So we're just going to have our binary kind of alphabet stuff. It'll have our typical triangle. It'll have a blank symbol. And it'll have a semicolon as well. And it'll also have parentheses. And it'll even have a comma. So it looks kind of weird because I'm separating out the symbols by commas. But this comma is a character in the alphabet. So, I mean, this is our alphabet, and we're at that point where I can just kind of say, I can just kind of make my alphabet whatever is convenient. And this is really the convenient alphabet. Parentheses are convenient, so I'm going to throw them in. Commas are convenient, so I'm going to throw them in. At this point, I can do that, because I've proven equivalence between different alphabets. Now, that said, the alphabet for M, on the other hand, is going to be any number of characters. And I don't necessarily have to do this. You know, I could build a universal Turing machine for the set of Turing machines over a fixed alphabet, and that would be just as good as of a proof. But it's not that much harder to make a Turing machine that works over any finite alphabet, and I think that would be more kind of impressive to the viewer. And so I'm going to do it like that. I'm going to have M be an arbitrary sized alphabet, even though I know I could just kind of take whatever M I want, collapse it down to 2 symbols if I wanted to, and then assume every Turing machine input has 2 symbols in their alphabet. But I won't do that. I'll assume it has any number of characters. But what I will assume is that the characters are all kind of from the same set, and that they're signified. So the Turing machines can be any number of characters, but the characters are all from some common set of characters, some common infinite set of characters. Like maybe take ASCII, right? ASCII's got tons of characters, so maybe all of our Turing machines use characters in ASCII. You know, maybe it uses 12 of them, maybe it uses 8 of them, but it uses some characters from this common set, which I've numbered. And in addition to that, I'm also going to assume that the states of the Turing machine will be from the same set. So states for any Turing machine will also come from this set. So, I mean, I need symbols for the states as much as I need symbols for the characters. They serve a different purpose, but they can come from the same infinite set. It doesn't really matter what they are. And so the idea is going to be that, you know, let's say that my Turing machine, you know, let's say that my infinite set, big set of characters is, I don't know, maybe like just the English alphabet up to Z, right? So there's an implicit numbering of these, of these characters. This is obviously not an infinite set, so just maybe like, you know, let's just suppose that it continues forever somehow with other symbols. If my Turing machine's alphabet if my Turing machine's alphabet is like, let's say, just, I don't know, D, F, and L, you know, it doesn't necessarily have to be the first three. I'm just going to pretend you know, the bottom line is if the alphabet is three symbols, there's no harm in pretending that it's the first three symbols, right? So I'm just going to pretend that D's are A's, F's are B's, and L's are C's. And so because of that, I can instead of thinking about the symbols at all, I can think of instead of thinking about it as A, B, C, or D, F, L, I can think of it just as 1, 2, 3. And so, in fact, by doing this, I can assume that that all of the states and symbols are integers. More or less, right? They're integers that represent symbols, but they're specified by integers. And so, also one other convention I'm going to say is that you know, let's say that the states for M, remember, the states and symbols are all coming from the same set. So if the states of M are like B and Z or whatever, let's say there's only two, I'm going to assume that instead it's going to be 4 and 5. So not only is it still going in the order, it's going from the order continuing from this. So let me summarize that. The idea is that so if M is equal to sigma q delta, we'll assume that sigma is equal to 1, 2, 3, dot, 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 up to the size of sigma. And what I mean by that, by the way, I've done this a few times. I've said this before. I've used these bars a bunch of times without explaining it. When I put bars around a set, I mean the number of elements. So if I put bars around a set, I'm referring to its cardinality. That is, the number of things inside of it. And if I put bars around a string, I'm referring to the length of the string. I've done this a bunch of times. I've used these bars all over the place, and I've kind of hoped that I think people have probably seen these bars and gotten an understanding of what I mean by them, but I felt like I should say it explicitly. You know, and if you put bars around objects in math in general, you're referring to kind of their magnitude, kind of in some sense. The exact nature of what magnitude means for the object is sort of context sensitive, depending on what you're putting bars around. But you know, you can see a number of things in a set, length of a string. These are very related ideas. They're kind of size. So anyway, that's what I mean. So when I say sigma is equal to 1, 2, 3 up to sigma, I mean it's 1, 2, 3, dot, 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 up to just however many things are inside of it. Also, then q is equal to, it's going to start counting up from however many things are in here. So it'll be sigma size plus 1, sigma sized plus 2, dot, 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 up to sigma sized plus however many things are actually in q. So this is going to be my standard. Finally, oh wait, there's a couple more things. Finally, remember my complete description for a Turing machine is going to need to include symbols, obviously, and states, but it's also going to need to include, remember, this delta function also spits out directions, and there's 3 of them. So I need 3 more symbols to denote the directions. And so finally, sigma plus q plus 1 and sigma plus q plus 2 and sigma plus q plus 3 will stand in for the 3 directions. that a cursor can go. So, and then also, wait, one more bit of convention. Sigma plus 1, I'll always interpret sigma plus 1. Maybe I'll just put it here, actually. Sigma plus 1 will always be the initial configuration, will always be the initial state. And the last 3 numbers in Q will always be the halting states. Right, the acceptance state, the rejection state, and the actual just ordinary halting state, respectively. I'll always assume that those are the last 3 states. So that's kind of like, finally, I've sort of fully specified, I think, everything I need to. And of course, integers are integers, but my universal Turing machine alphabet doesn't have integers. It has 0 and 1. It only has 2 of them. So what I'm going to need to do is represent them in binary. So all of these integers will be represented in binary using a certain number of bits, depending on sigma and Q. In particular, if you remember that video that I did on the codings of alphabets, you'll remember that the number of bits that I'm going to need, that is the number of symbols that I need to denote a single integer, is going to be log base 2 of the size of sigma plus the size of Q plus 3. That is the number of symbols total, the ceiling of that, this many bits. And I didn't completely spell out how to count in binary or do a conversion to binary in that video, but the idea is really simple, right? If I'll start with 0. How many characters do I have to represent all the integers? I have 2, 0 and 1. So I'll start counting. So 0 is what I'll call 0, and I'm not going to write down all of the correspondences. But after that, I'll have 1. That'll be 1. And now I'm out of symbols. So I have to kind of now I have to use 2 kind of characters. Now I'll say 1 0. This will be 2, right? So I just kind of start over the 0 count. I start over counting in this. I start over counting in like the 1's place, and now I start counting in the 2's place, where usually this would be called the 10's place, but since I'm counting in binary, this is now the 2's place, and then this will be the 4's place. So this is how you count in binary. You go 0, 1, and then you reset. You put a 1 over here, 1 0, 1 1. Now you're out of room in both these slots. Now you move over here, 1 0 0, and then you restart the process with 2 bits here, 1 0 1, 1 1 0, 1 1 1, and then you're out of space again. And so now you move over to the, well, let's count. This is a 3. This is a 4, 5, 6, 7. And so this will be the 8's place. And if you notice, that's 2 to the 3rd. So this is the 1's place still. The 1's place is always the 1's. The 1's place is always the 1's place. The 2's place is what would normally be the 10's place. The 100th place is now the 4th's place. The 1000th place is now the 8th's place, and so on and so forth. But this is how you count in binary. It's really simple. Now, we want all of them to be the same length. This is the number of bits we'll need. That is, this is the number of places, the number of place values that we need to represent this many bits. So what I'm going to do is I'm going to pad with leading zeros to make all binary representations the same length. So I mean, I'll put like, if I need 4 bits, then I'll put like zeros like this. I talked about this kind of thing in my codings video, but definitely worth reviewing, especially since that's I think that's the least viewed video in this whole series so far. So that's what that is. So everything will be the same length, and then it'll be able to So basically, if I can just specify the size of these two sets, then I've fully specified sigma and q. So now let's talk about the actual description of M. So the description of M will be 3 strings separated by commas. First will be the size of this. So this is the first guy, which is the size of the alphabet, and then a comma, and then the size of the states. And so note that these two things, if I just start out with these two things, these two numbers in binary, mind you, these two numbers fully specify the set of states and the set of symbols. If I just give you these two numbers, by my convention, I've actually given you the entire alphabet and the entire set of states. And the only thing that's left still is a description of the transition function is still needed. So how do I do that? How do I describe the transition function? Well, the transition function, remember, is kind of a table. It's kind of a set of inputs and outputs. But I can always represent it as kind of, so delta will be represented by a set of pairs of the form, it'll look like this. So there'll be like a sigma and a p, or sigma and a q, I guess I usually start with for some reason. And then it'll be another triple over here. It'll be a lambda and a p and a delta and a d. So it'll be 2 parentheses, and remember, parentheses and commas are part of my universal Turing machine's alphabet. And then these guys, these are symbols and states and directions. These are all, of course, represented in binary. And conceptually, because my description of this Turing machine leads with sigma and q, the Turing machine will be able to do a calculation and then figure out from these two numbers that I'm given, which are separated by commas, how many characters the binary representations of things in delta are going to be. So it will make that calculation, and then it can move over here and figure out, like, okay, I need to go this far to get to the state from the symbol, and then it knows all of that stuff. These are represented in binary. And of course, what does this represent, actually? This corresponds to the instruction that the function delta of sigma and q is equal to lambda p d. So that's what this represents. So if I just basically, it'll be a set of all of these. It'll be a set of all the instructions represented this way, surrounded by commas, surrounded by parentheses, I mean. So the whole set, so it'll be like this, and then instructions in this form here, and then another parentheses. So to summarize, and that's the full description. So to summarize, M is going to look like this. I'll use little m just to make a distinction between the actual Turing machine and the program that represents the Turing machine, the string. It'll be size of sigma, comma, size of q, comma, and then it'll be a big parentheses, and then another, and then it'll be the pairs like this. So it'll be like, maybe I'll just put, like, these will be numbers. So it'll be like 1, and then, I don't know, like 8. And then it'll be in here delta of 1. Whatever that is. Yeah, so this is one object, and then another one would be like, I don't know, 2, 12. Dot, dot, dot. And then finally, the last one I'll imagine will be, size of sigma, size of sigma plus q, um, comma, delta of that stuff. It'll look like this. So the complete set. So it's long. I mean, it's a long string, but this is a program. You can see how this is a program. So this is our standard. This is how we're going to represent a Turing machine. And every Turing machine represents this way. And maybe as an exercise, you should think to yourself, don't try to make a Turing machine for it, but write down an algorithm for. Maybe I'll write this as an exercise. And by the way, I'm re-recording this. This is like I've already made the videos past this, and I actually kind of skip the step in which this needs to be done. But this is kind of the first step necessarily of how to make a universal Turing machine. Exercise. Describe an algorithm for deciding if a given string codes a valid Turing machine. So I'm giving you a string, and I'm asking you, does it code a valid Turing machine in the sense that does it represent a Turing machine in this form? So, you don't have to do this exercise. I'm just giving it as an exercise more or less because, I mean, it's kind of worth thinking about, but also I'm giving it because I didn't feel like thinking about it in my proof that follows this. So technically, you do need an algorithm for this. But my hint to you is that you first need to calculate the logarithm of this plus 3. That's what you need to do first. But anyway, that's our convention.